So this is the op-amp we have, and we have analyzed it. We have sort of beaten it to death. We know what it can do. What are the disadvantages of this? Now we know that it can do some things, right? It can, first of all, we already said that if we have only a capacitive load, we can use a single transconductance stage as an op-amp. So this is good only for driving capacitive loads. If you put a resistive load, then you have to increase the GM by so much to get a large DC gain that this is probably not the right way to do it. Did any of you attempt the assignment, the single stage op-amp? Okay, you still have 5 more days. You can start on the 4th day. Let's say you design this and you get a DC gain of 50. Now I want a DC gain of 1000. What do I do? Huh? Length of PMOS. So you go on increasing the length of PMOS and the gain will improve. These two. What is the DC gain of this device? It's GM1 by GDS1 plus GDS3. So if I increase the length of PMOS, I will go on reducing this. At some point it becomes GM1 by GDS1. So I can also go on increasing the length of NMOS and I can reduce this also. But now I am not talking about going from 50 to 70. Okay, I am talking about going from 50 to 1000 or maybe 2000 or some large increase. You have a feeling that this is not going to cut it, right? Because you have to increase the length by 50 times. That's not happening. Okay. First of all, even if you are able to do it, the parasitics will increase so much that your phase margin will deteriorate drastically. So what else can you do? So this is the point at which we need a change in architecture, not just playing around with parameters of the given circuit. What can we do? Cascade. Okay, that is one possibility. So each has its own DC gain and I get the product of 2. So if I was able to do 50 with 1, I can do 2500 with 2, roughly speaking. Okay. What else can I do? First of all, let's analyze this little more. I have the differential pair which takes in the differential voltage and gives me some current variation. Okay. The current in the 2 drain branches here and here are I0 by 2 in quiescent condition, but they have some plus and minus variation when you apply a differential input. So this is the part that responds to the input and this is the active load. Okay. Now this entire circuit is like a voltage controlled current source or a transconductance with a certain transconductance GM and a certain output conductance G out. Okay. Which part contributes to the transconductance? The differential pair. Okay. So this is GM1. And what contributes to G naught? Active load? Both of them. So both the differential pair and the active load. GDS3, sorry. So if I look at this differential pair, it's contributing a transconductance of GM1 and an output conductance of GDS1. And the active load contributes a conductance of GDS3. Okay. So if I somehow keep the same structure, but reduce GDS1 and GDS3, I'll also have a higher DC gain. This is very much valid. In fact, that's the one that we are going to do next. But because the other topology is so close to this, we can analyze it more easily and we'll do it first. Okay. So I need something like this, some differential pair, which still gives me a transconductance like GM1. Okay. But gives me a much lower output conductance. So similarly, active load with a much lower conductance. So what do I do? So I use a common gate amplifier to boost up the output resistance or to reduce the output conductance. Okay. can we not degenerate with the resistance? Okay, that's a good question. So suggestion is I will degenerate with resistance. So what will happen now? Okay, first of all, what changes now? I had originally GM1 by GDS1 plus GDS3. So how will this expression change? And what else? Roughly speaking, this is what happens. Okay, GDS1 by GM1 RS. Okay, so in fact it doesn't increase the DC gain, it reduces it because you have left this part untouched. Now you can degenerate this also. Okay, now if you have the same amount of degeneration, let's say GM3 RS3 is the same as GM1 RS. Okay, you have not changed anything. The DC gain doesn't change if you degenerate it. It will increase the output impedance, but also it will reduce the transconductance. Okay. What I would like to do is to keep the transconductance the same, but reduce the output conductance. That's what I do when I increase the length and width. Okay. So I have the same bias current, I increase width and length, let's say by a factor of 2. Then I have increased the value of output resistance. But I have kept GM the same, assuming the square law model. Okay. So a common gate amplifier, we know, works as a current buffer, and that's what we want here, because we have this differential pair. If I apply a differential voltage to it, I get some current variation around the bias value. Okay. Now what is a common gate amplifier? This is biased at some fixed voltage, or incrementally it is grounded, and there is a certain bias current flowing through the transistor. Okay. And I apply a signal current here. Now that signal current comes out with a gain of 1. Okay. If the source that is pushing I signal has a certain impedance RS, from here it looks like a much higher impedance. Okay. That's what the common gate amplifier does. Now this is using an NMOS transistor. Of course we can use a PMOS transistor also, in which case I will have some I bias, some V bias here, and the signal current going this way. Okay. And what is my signal current here? This ID. Okay. This is the part in response to the input differential voltage that I have to pass through the common gate amplifier. Okay. So will I choose an NMOS common gate or a PMOS common gate? Why? Why will I choose an NMOS common gate? Then what's so good about the NMOS common gate? The thing is, of course, this is just a signal current and I need to provide this bias current also. Now, what I have here is the bias plus signal in the correct direction for the NMOS transistor. Okay, so it looks like it is more convenient to use the NMOS transistor. Now, I can also use this. I just have to make the appropriate arrangement for bias. That's all. Okay. All I want is this I sig, that is this ID here, to flow through the common gate amplifier. I can do it for both cases. In PMOS case, I have to do a little more work to get the biasing arrangement correct. In NMOS case, I had to apply this bias and also add the signal. Now, if I look at what I have, the NMOS differential pair, I have the bias plus signal right away. So I can use the same current to bias this. Okay? It's just a matter of convenience. Is it okay? So that's what I'll do. So let's say first I'll choose to use the NMOS common gate. Let me just call it V bias N2. Now clearly I cannot use this with the active load as it was, because then I would have reduced the output resistance of one side but not the other side, which will dominate anyway. Okay. So originally the active load was this. What do I use instead of this one? PMOS Cascode. So which side will I do that? M3 or M4 or both? Both. So I would like the mirroring also to be accurate. Okay. So what I use is a structure that we derived for biasing, but then later extended to a cascode current mirror. Okay. So this is a cascode current mirror, and I can use this as the active load. What's that? Oh, this one. Okay. The question is, why can we not use the original active load? What's the answer? What will be the DC gain of this? Okay, what is one component of the output resistance that dominates here? GDS of M4. Okay. On the lower side, we have boosted the output resistance, and let's assume we have boosted it to such an extent that it doesn't matter. What will be the DC gain? GM1 by GDS4. This is of course an improvement over the previous case, but not an order of magnitude type of improvement. Okay. Previously we had GDS3 other plus GDS1, and we have got rid of this. Okay. So this and this can be expected to be in the same order. May not be exactly the same, but they will be of the same order. Okay. Again, to lower GDS3, you will have to increase the length of M4, which you don't want to do, at least not by a large factor. So that's why I don't want to use the original current mirror active load. And in general, it doesn't make sense to improve one thing a lot and then leave everything else screwed up the way it was. Okay. So I have this. I have used common gate amplifier on top of the input differential pair, and also I have used a cascode current mirror. Okay. I will label these M3, M4 as before, and maybe these form M5, M6, M7 and M8. Okay. V bias P2 and V bias N2 are biased such that all transistors are in saturation region. Let's worry about exactly how much it is afterwards. Okay. In fact, we have dealt with this in the context of current mirrors, and we can make a circuit to generate those voltages, but let's assume that it's biased appropriately for now. Let's evaluate some basic characteristics before going on to more detailed analysis. Thanks. Okay. Now again, what will be, if I had absolutely no mismatch, what will be this voltage? What will be the output voltage? It will be the same as the other side. Okay. We can use argument similar to the one we did before. If it happens to be larger, you get inconsistent conditions between NMOS and PMOS, or also if it is smaller. The only point where you get a consistent solution is these two nodes being equal. Okay. So let's connect a voltage source of that particular value, VDD minus VGS 3, whatever it is. So what will be the current here? 0 in the quiescent condition. Now if I apply a differential voltage VD by 2 and minus VD by 2, what will be the output current? How will we analyze this? So first of all, what is this voltage? 0. Why is it 0? The impedance looking in here is what? See, last time we analyzed the circuit, if the differential pair is terminated by small resistances, the tail node voltage is 0. What is the impedance looking up here? 1 over GM5. Okay. And here, same, 1 over GM5. So it's terminated by a small enough resistance that this is close to 0 volts. Okay. So that means that what is the incremental current through M1? GM1 VD by 2, and here it is minus GM1 VD by 2. Okay. And this current goes through M7, M3 and also gets mirrored from M4, M8. Okay. So the net output current is GM1 times VD. So the transconductance is GM1. This is what we expected by construction, but we just analyzed to make sure that that is indeed the case. The one thing I want to say here is that already the circuit has got quite complicated. We have 9 transistors, and if you put GM and GDS of everything and try to write equations and solve it, it becomes very difficult. So you should be fluent enough with the basic circuits so that you know what to neglect when. Okay. That's the only way you are going to get through more complicated circuits. Okay. So transconductance we know. What is the output conductance? For output conductance, we have this bias, we apply an increment over this, the input increment is 0. Okay. So let's say I apply an increment on top of this. And I measure the current that's going here. Okay. And of course, I don't have the input small signal increment. What is I test? So what really happens here? First of all, the behavior of this circuit is exactly same as the basic differential pair, except that on both sides we have slightly more complicated circuitry. Okay. Now M4 and M8, they form a cascode current source. What is the output resistance of the cascode current source? Output conductance. So the output conductance is approximately GDS4, GDS8 by GM8. There will be other terms which we will neglect. Okay. So what was usually GDS4 has become this one. Okay. Then what happens on the other side? What is if I apply V test here, what is the current that flows in here? So GDS1 times GDS5 by GM5 times V test. Is that what flows into the drain? Again, that current division happens like before. Now, if you try to analyze it exactly, it's even more complicated now because of the presence of more transistors. So, we will do it partly. The actual output resistance of a common gate amplifier is, let's say, if I was looking up here, I also get these two terms. Okay. So, but these two I always neglect because that gives me unnecessary complication in the algebra without adding much to the answer. Okay. So, first of all, what's the impedance looking into the source of M1 like this? 1 over GM1. So, what is the impedance looking into drain of M2? Huh? 1 by GDS2. 1 by GDS2. 2 by GDS2. Okay? Because it is degenerated by, this is M2. And M2 is degenerated by M1. Okay? So, the degeneration impedance is 1 over GM1, which is the same as this. So, in this case, clearly I can't neglect these two, right? Okay? I can neglect these two only if this GM by GDS ratio is large. If it is 1, I can't neglect that. So, looking in here, I get 2 by GDS2. Is this part clear? This is exactly what we did with the differential pair, no difference at all. Okay? Now, M6 is degenerated by 2 by GDS2. Okay? So, what is the impedance looking down? Two by GDS2 times GM6 by GDS6. Okay. In this case, I can neglect the other two terms because they will be smaller. Okay. Is this clear? If it's not, let me know. I'll repeat that. So, I have this part, I have drawn only the lower half of the circuit. Okay. Now, looking up here, I have a resistance of 1 over GM1. Okay. This is because here it is a low resistance and here also it goes into a diode connected type of transistor. So, here also it's a low resistance. So, looking here, I only have 1 over GM1. So, looking down here, I have to analyze this circuit. I have M2 and 1 over GM1. So, what is the output resistance looking in here? This is degenerated by GM1. So, if it is some R, what is the resistance looking through this? So, we know this already, right? It is GM2 by GDS2 times R. Plus the RDS of this. Plus 1 by GM1. Okay. GM2 is the same as GM1 in the quiescent condition. So, this goes away. I have 2 GDS2, 2 over GDS2 plus 1 over GM1. Again, I neglect this in favor of the other two because it is going to be negligible, right? GM1 is much more than GDS1. So, GDS2, so looking up here, I have 2 by GDS2. So, now I analyze M6 with whatever is degenerating it. Okay. So, M6 is degenerated by 2 by GDS2. So, what's the impedance looking down here? So, it's GM6 by GDS6 and GDS2 by 2 plus 2 by GDS2 plus 1 by GDS6. Okay. So, I get 2 times GM6 by GDS6 times GDS2. That is the first term. Now this, because of GM6 by GDS6 ratio, which is very large, is going to be larger than these two. Again, I neglect these. Okay. So looking down here, I say that I have an impedance of this much. Is it okay? It is 2 times the resistance if I had only this cascode. Okay. It's exactly like with the differential pair. I look in here and I don't see GDS1. I see GDS1 by 2. Is this okay? Now I do neglect the other terms because they are indeed small compared to this. So if I apply an increment of V test, certain I test flows, and some part of I test is because of the current that flows down, and some part is because of the current that flows up. Okay? I call it I up and I down. And what is I down now? Now that we know what the impedance is looking downwards, what is I down? What is it? So that's the resistance. I want the conductance here. Okay. Okay. That is the current that flows down. What is the current that flows up? Plus I down flows this way, and this is a current source. Okay, so it flows back into M1 and gets mirrored all the way through M7, M3 and M4, M8. Okay, so this is again something that's familiar to us with the differential pair. So it goes like this, and the same thing gets mirrored here also. Okay, so this plus I down. So finally we have the output conductance to be what? Okay. This is in contrast to the differential pair which had GDS1 plus GDS3. So each term has been reduced by a number which is of the order of GM by GDS. So we have a reduction in the overall output conductance of the differential pair. This is how we get a larger DC gain. Okay. The DC gain is the ratio of transconductance to output resistance. Okay. By reducing the transconductance to output conductance. By reducing the output conductance, we can boost up the DC gain. So DC gain now is okay, and previously it was for the simple differential pair, it was GM1 by GDS1 plus GDS3. Okay. So we have gone from some number which is of the order of GM by GDS of a single transistor, okay, to something that's of the order of GM by GDS square. Okay. So the DC gain you get from this is similar to in order of magnitude similar to if you had two stages in cascade. Okay. Is this clear? Is the analysis of DC gain clear? Now, this topology is very similar to the differential pair. So, the analysis of every parameter will be very similar to what we did in the differential pair. Okay. But because we have more transistors and more nodes, we have to selectively neglect some things during the analysis so that we don't get overwhelmed by the algebra. So, we have managed to make an op-amp with a higher DC gain. So, this we have the supply voltage and we need to provide for these two bias voltages also. Okay. This is the output. Now, this is known as a telescopic cascode op-amp. Cascode because we have used cascodes in the amplifier, and it's called telescopic because we have things stacked on one another. And the term telescopic is used for anything that has many things stacked on each other. Okay. So, we know the DC gain. And we know the transconductance, it's the same as before. So, let's say you had a load capacitance and you had the simple differential pair op-amp driving the load capacitance. You replace that with the telescopic cascode op-amp. What happens to the unity gain frequency? It's the same. Okay. But the DC gain increases. So, if you plot the magnitude response of the op-amp by itself, originally perhaps it was like this, and now it will change to something. It will continue along this line further and give you a much higher DC gain. Okay. The question is, why will the unity gain frequency remain the same when we have added so many transistors and their parasitics? I am now assuming sort of zeroth order analysis where the capacitance is dominated by whatever load we have. Okay. In that case, it will not change. That's true. The transistor size in a cascode amplifier and in a regular amplifier may be different. So, internal frequency response will be different, and this has so many other nodes. Okay, at each node you expect a parasitic capacitance. So, you expect a lot more poles and zeros in this case than in the differential pair. But ignoring all of that, you do get to a first order the same unity gain frequency. Okay. If you wanted to improve the precision of your circuit, this is what you would do, right? You are not concerned about speed now. That's a different optimization altogether. Your DC gain was too small, so your precision was too small. The precision of the feedback network after it settles into steady state. So, then you have to increase the DC gain, and this is what you will have to do. Okay. So, we will stop here. The only thing I want to ask is, how will you use a PMOS cascode? Let's say I started with NMOS cascode because it was convenient. How will I go about using a PMOS cascode? His suggestion is this, okay. I'll draw only one half, and I want finally a picture like this. I want this bias current plus the signal current that is flowing in. And his suggestion is to use this. So I have a certain bias plus increment here, okay, and that can be mirrored into another transistor, okay. So I'll have to do exactly the same thing on the other side also. This is also a PMOS cascode. Then what do I do? Let's say I have I0 by 2 plus ID. I0 by 2 plus ID, and let's assume identical current mirrors. Sorry, minus ID, of course. So now here I have I0 by 2 minus ID and I0 by 2 plus ID. It's as though I use the PMOS differential pair. Okay, I have just changed the direction of the current. Now what do I do on this side? So I can use an NMOS cascode. Okay. So you can see that very quickly you can get very complicated circuits. Actually, let me not do this. Let me not show these connections first. That's why I wanted this to be the plus terminal of the op-amp, this to be the minus terminal. Now on the bottom I have drawn the cascode. So which side will I mirror from which side? There are two possible terminals for the output, this one and this one. Okay, I can mirror from this side to this side or from right to left. Which side will I do so that this to be the positive input of the op-amp and this to be the negative input? Right side should be the output. Is that correct? Yeah. So in this case it's very easy. I had also shown this. So if I have a differential increment here, I have plus ID here and plus ID here. Okay. So that means that it goes into this node and tends to increase this voltage. So it has to be like this. Okay. So because in this case you fold the current that comes out of the differential pair, this is known as a folded cascode. Yeah, current is folded down. So this we will discuss in detail, and actually there is another way of making a folded cascode. Okay. Again, I think I am out of time, so I am going to stop here. In fact, this current mirror is not what is frequently used. Okay. We will discuss the other technique tomorrow. That's all for today.